Hi, my name is Chima, and today I'll be solving Leetcode problem 108, convert sorted array to binary search tree. So, in this problem, we're given an integer array nums where the elements are sorted in ascending order, and our goal is to convert it to a height balanced binary search tree. And just to explain what a height balanced binary search tree is, if I hover over this icon here, it says height balanced binary search tree is a tree in which the depth of the two subtrees of every node never differs by more than one. So, for example, if we start from our root node, the depth of the two subtrees, so of the left and the right subtree of every node, never differs by more than one. So, for example, you can see from our root node, the maximum depth of our left subtree here is 2, and from our root node, the maximum depth of our right subtree here is also 2. So that's basically what it's saying here. So this is a good question to understand the properties of binary search trees, like in general, and it's very intuitive and very it's very intuitive because the array that they give to us is sorted in ascending order, which will help us define the properties of a binary search tree. So, the binary search tree, one of the main properties is that every node, at every root node, or at every node, its left subtree and its right subtree, or its left child and its right child, they must adhere to specific properties. So, starting from a parent node, its left child must be less than the parent node's value, and the right child must be less than the parent node's value. Or sorry, must be greater than the parent node's value, and this property has to hold for every node within the tree. So, as you can see here in example 1, we have a node of 0 here. Its left child is 3, which is less than its parent, which is 0. We have a right child of 9, which is greater than its parent value of 0. And that property holds for every node within the tree. So here, from -3, we have -10, which is less than -3. From 9, we have 5, which is less than 9. Okay, so now you might be thinking, how do we convert an array to a binary search tree? And it's pretty intuitive, since they give us input in ascending order, right? So since the input is in ascending order, and we have to create a height balanced binary search tree, if we were to split our input in half, then we know that half of our input is going to be greater, or the right half of our input is going to be greater than the left half of our input, right? So why don't we say that if we split our input in half, then the right half can belong to our right subtree, the left half can belong to our left subtree, and that satisfies the binary search tree property that I just explained, where at every node, the left subtree must be less than its parent, and the right subtree must be greater than its parent. So, to make things a little bit more intuitive, I'm gonna copy this example here, and I'm gonna go into Paint and draw it out. So here, so we had n equals 10, -3, 0, 5, 9. Right, so as I said, we split our input in half. So when we split our input in half here, we see that we have 5 elements, so splitting it in half will give us 2.5, and we just take the floor of that as we're working with array indices here. So that'll give us 2. So this is going to be our middle elements here, or our halfway point. And then, as I said, our right subtree would contain all the elements to the right side of our split, and so this is going to be our right subtree, and our left subtree is going to contain all the elements to the left of the split. Right, and you can see how nicely this works in terms of actually building out the tree, and in terms of maintaining the binary search tree properties, because if we were to recursively do this method which I just showed on both the right subtree and the left subtree, we'll quickly find out that this property is able to help us build our high balance bounding search tree while maintaining the fundamental properties of a binary search tree. So I'm going to do one example for the right subtree and to show you how that would work. So if I were to recursively partition this array to build my right subtree, I'll be left with 5 and 9, right? And then when I split this 5 and 9, so let's say this is n0, say this is n1, right? So when I split this array into 2, that's what we get. We get 2 divided by 2, which is 1. So this would be our new mid, right? And then from here, our right subtree is null, but our left subtree is 5. So RST equals null, right? And just looking at this example here, right, you can kind of see, or not kind of, you will see how I just you utilize this method recursively to actually build the high balance binary search tree. Because if you look at this example here and go back to the example on Leetcode, you can see here that when they split on the right subtree, starting from the roots, the subsequent tree that's built is one that has 9 as its new roots and 5 as its left child, which is what I showed you here, where you have 9 as new roots. So I'll call this roots rather than mid. Roots. Well, it's technically mid, but it can be root mid. So it's going to be 9 as a roots and 5 as a left child here. So following this example, we can recursively build our entire high balance binary search tree from the given input. So let's go about writing this in code, and I'll kind of explain the code and the reason as to why I'm writing specific code as I do it. So in order to compute the midpoint, right, what do we need to know? We need to know where we need to know the length of our array, and also where the middle value is going to be based on that, right? So right now, from the start, like, we know the length of our array is going to be 5, right? So yeah, 5. But remember, this is recursion, right? Like, we're making recursive calls, right? So we can't have a static length. Our length needs to be dynamic based on how we're going to be building our subtrees. So we're going to use pointers to help us to do that. So if I say our left pointer is going to start off at 0 and our right pointer is going to start off at len nums -1, we can now recursively build this high balance binary search tree. So say def build tree, so it's going to be our helper method to build our tree. And what do we need to do? So as I said, we need to find the midpoint. So midpoint is going to be left plus right. Then in Python there's a nice operator like that to get the floor division of this operation. In other languages you can probably do something like, math the floor left plus right over 2 or something like that. But like in Python there's this double backslash operator here. So we get the midpoint here, and then now that we have the midpoint, what do we want to do? So we want to make a new tree node. So tree tree root node equals what? New tree node, and we want to put the value that we found at the midpoints. Nums the midpoints, right? So we make a new tree I was going to say tree node, not tree root node. A new tree node based on the value that we found at the midpoint, right? So when we find the value at our midpoint, this is when the recursion starts. We want to build our left subtree and build our right subtree based on where our pointers are at. So from the root node, or from the midpoint, we build our left subtree by so let me explain it here a little bit better. So from our root node, or from our mid node, so if this was mid and this was left and this was right, in order to build our right subtree, what do we need to do? We need to shift our left to mid plus 1. So left will now be over here. Right, and we just need to take this partition into our recursive call. Right, and if we were to build our left subtree, it's just going to be the opposite, where we'll take our right to be mid minus 1. This is very similar to a binary search type of algorithm. So let's go about solving it here. So we say TreeNode.left equals build tree, and as I said, to build our left subtree, all we're doing is moving our right pointer to mid minus 1. So our left pointer stays where it is, and our right pointer is now becoming mid point minus 1. And to build our right subtree, you just do the opposite. So left plus 1, right stays where it is, right? And then once we're done with all this, we can just return the tree node, right? Because the tree node is going to have the result. Once we backtrack, the tree node is going to have the result of each recursive call that was placed on the stack. I'm not really going to explain how the stack or how the recursive stack is going to be built as we're making the recursive calls in this video. I think that's something that's for another video, and also I'm not really going to explain how backtracking is going to work here. And now one important thing to note here is that as with every recursive implementation, we need to have a base case here. So our base case here is going to be whenever we exhaustively search either the left subtree or exhaustively search the right subtree. So we can say that at any time our left pointer is greater than our right pointer. So if left is greater than right, return none. And yeah, so that just means that we've hit our leaf node. Once we're done, we just say results equals build tree. Pass in our left, pass in our right pointer. Just return results. If I run this, so for case 1, for case 2, I pass. Okay, so that's my mistake. So node.right, so it has to be midpoint plus 1, not left plus 1. So if I run this again, submit it, now this passes.